All right. So let's take a look at this one right here. Okay, let's look at some series again, because it's been 2 days since we've seen series and sequences, right? Unless you've been doing your delta math. The first one, it's not P series, right? It's geometric. Okay, is this geometric? N over 2 to the n? No, it's not geometric. Okay, even if we use the nth term test, it will be an inconclusive type of test. At the end of the lesson, we'll be able to determine if this part right here, if this one converges or diverges. We'll be able to tell by the end of the lesson. The same thing with this one. This one's P-series, but this one actually is not P-series. Okay, this one here is not in the form of P-series. So once again, at the end of today, we're going to learn how to do it. The same for number 3. Our goal in this case is to compare a type of series, whether it's P-series, geometric series, or something to compare it to be able to determine whether it converges or diverges. Okay, bless you. So here's how it is. When you're given a problem, okay, let's say A of n. Okay, this is your original problem, your OG. Okay, that's your original problem. Okay, and it's not a geometric series, or it's not P-series, or you necessarily don't want to do the integral test because that would take way too long, or you can't necessarily integrate, and the nth term test doesn't work. Then we're going to use what we call the comparison test. You're going to get a different series to compare to the original series. And if the different series converges, here's a catch. If the different series is larger than the original series, and the different series converges, then so does the original series. And I know all of this probably doesn't make sense. Okay? The same goes. If the smaller series diverges, meaning if you're comparing this is a comparison, then your larger series must also diverge. Okay, these two statements are really important. If your larger series converges, then your smaller series converges. Okay, this is your original series. This is the original series. So you want to compare and contrast. That's up to you. I would write these two statements if it's not there already.
It's on page 14.
Page 14, thank you. All the two sentences are on page 14? Thank you. No, it's series and sequences. If the comparison is larger and it converges, bless you, then the smaller series must converge. And I'm going to put down a few things. Inconclusive. It will be inconclusive to say if the larger, or if I should say if the smaller, converges, okay, meaning if the smaller comparison. That means inconclusive. Okay, the comparison has to be larger and converge for the original series to also converge. If the larger comparison diverges, then it's also inconclusive.
So the original one is always the smaller?
No, not always. Okay, for converging, the original one, you want it to be smaller. For diverging, you want the original to be larger.
So you can take which one it is?
You'll see an example. Okay, probably doesn't make sense and this is confusing, but we'll come back to it.
Oh, this is bigger. Okay, so we just replace the bigger one. So if it has an N, it's smaller.
All right, let's do an example because this is probably confusing, right? But let's do an example here. All right, what does this kind of look like? What does this series kind of look like? It looks like geometric, but is it a geometric series? No, it's not geometric because of that 2 plus, right? Therefore, we can't use geometric series test. If we use the nth term test, what will that limit equal to? So what does that mean? Inconclusive, or it does equal to 0 in this case. So we can't use the nth term test to determine that. If we use the integral test, it's going to be very challenging to integrate. Can I use p series? I can't, right? It's not in the form of 1 over n to the power of k, where k is the constant. So I can't use neither of these tests right here, so we're going to use what we call the comparison test. As you guys said, it follows very much like a geometric series, right? Like which geometric series? 1 over 3n. So how about we compare that series to 1 over 3 to the n? It's a possibility. And what do you know about 1 over 3n? Does this converge or does this diverge? It converges. Why? It goes to 0. The limit, well, that still would be inconclusive. By which test do you guys know that this converges? The geometric series test, right? Because the ratio equals to 1, or 1/3, which is less than 1, as Victoria said, right? That's the geometric test. But in order to determine if our original series is convergent, just like this one here, in order to converge, right, the larger series has to converge in order for the smaller to converge. So now we have to ask ourselves, is 1 over 3 to the n less than or greater than our original series? Which was larger and why? The one with the plus. Is it smaller or larger?
Wait, actually, no, that one's smaller. Oh, wait.
It is smaller.
Yeah.
So like this?
Yeah.
Yes. Why?
It's bigger on bottom and it's larger.
Eventually, the bottom is actually going to grow faster because of that adding 2, right? So 1 over 3n, is our comparison larger or smaller?
Larger.
So what does that say about the smaller series? It also converges. So by the comparison test, series converges. Let's try it. Let's start by plugging in 1, right?
Oh, because it puts next to denominator.
So if I plug in 1 versus 1 over 2 plus 3 to the 1. And then what if I plug in 2? Do you see how it's going to get smaller and smaller for the series here? That's all. You can also say that 3 to the n grows less than 2 plus 3 to the n. So if this is in the denominator, then it's going to create a smaller number, right? Questions over this stuff here? Did that make sense? Yes? Mm-hmm.
So back to like the reason why we chose the end test, that's because we're like going down a list of tests.
Yes, we were going down the list of tests. We can't use geometric series because this is not geometric series, right? I used the nth term test, but that still came back inconclusive. Integral test, can you integrate that?
No.
Integrate. Do you want to integrate?
No.
I don't either. And it's going to be very challenging to integrate that. You can't use U-sub. You can't use R-trig or integration by parts or partial fractions.
Right.
We don't know how to integrate that. So I can't use the integral test. Can I use P-series? Is this in the form of 1 over n to the k, where k is positive constant? So I can't use P-series. So now I have to use something else, which is what we call, in this case, the comparison test. Does that make sense?
Yeah.
Kind of.
Yeah, I'm just lost in the part where, like, what, so you have the original on the right, but on the left.
This blue part?
Yeah.
Uh-huh.
Like, how do we get there again? Like,
What does this look like? It looks geometric, but it's not geometric, right?
right.
And it comes very close to being compared to this one, because if you were to graph both of these, they would almost look very much alike, right? So that's why we want to compare it to something that basically has the same type of behavior,
Okay.
right? Does that make sense?
Yeah, I get it.
Other questions or clarifications? Yes, Jesselyn.
If you're ever doing something to the denominator that's like adding on to the number, then won't the compared to always be like
What if it was 3 to the n minus 2?
the other one would be larger, the comparison?
Let's see. What if it was in this form? Versus 1 over 3 to the n. Which one would be larger in that case? The one with the minus 2 would be larger, right?
Yeah.
And if this converges, then it's actually inconclusive. Because if the smaller comparison converges, it's inconclusive. So you have to use something else. Great question.
Wait, so you have to do something else? Like you would do a different comparison, or
You would do, could be a different comparison, or maybe a different test that we haven't learned yet. All right, try the next one. Try the next one.
job at experience.
Just small again. Comparison is small and what's small is like what?
Alright guys, so we start plugging in numbers. Put them up, just like we did. You don't have to do that many, right? You can just do at least 2, 3.
Smaller variances.
It's like you take that plus 2. Right, it's gonna
That's one with the
like the plus 2 and makes the denominator number bigger.
Yeah.
Whatever is bigger actually makes it smaller.
Make another R. What are you talking
I'm
about?
just like the one
I don't know.
comparison.
They're playing right now?
No,
Oh, yeah, actually, it might be in comparison. It's just larger. The larger one is
If comparison is larger, if the comparison is larger, right?
comparison is
If
smaller.
the comparison is smaller and divergent than the larger than
Say that one more time.
if the comparison is smaller,
The comparison is smaller.
What's your answer, George?
it's divergent.
No, comparison is small. Comparison is small. We're adding 2 to how big?
Yeah, I did that. Wait, no, I didn't.
Uh-oh, I hear a lot of mix-up. I hear a lot of mix-up. Who says the series converges? I don't think I saw anyone that says they converge. Who says it diverges? Who says something else?
Wait, I'm not done.
Just one person says Ethan?
1 over 2.
Just Ethan and you two?
Square
Andrew, what did you put down?
root of 4. Square root of 4.
Did you put convergence, divergence, or something else? You put divergence?
So square root of 4.
Yeah, the comparison.
Your answer?
Oh, no, I put my answer as inclusive.
You put your answer as inconclusive?
Square root of 4 right here, right?
The answer is inconclusive. It's inconclusive. In order to do a good comparison, since our comparison diverges, the comparison has to be smaller for divergence. The comparison has to be smaller for divergence. But in this case, since it's not smaller, it's inconclusive. Now, I can show you how to manipulate this a little bit to actually get a good comparison for this one. But it's just going to get trickier and trickier and trickier when it comes to problems like these. So why not just give you a way that it works 100% of the time, and you don't even have to think of, is it greater than, is it less than, does it diverge, does it converge? Bless you. You're just going to pick one comparison and then determine, based on that, converges or diverges. Do you guys prefer that? Let's find out. Okay, let's find out. All right, so once again, this one right here is inconclusive. Okay, inconclusive because our comparison series is not smaller. Okay, bless you. Our comparison series is not smaller. Okay, our comparison series is actually larger, right? Since it's larger and it diverges, therefore inconclusive. Does that make sense? All right. So now let's do, even though it falls under the same, the limit comparison test. The limit comparison test includes the comparison test, but this test works 100% of the time. Okay, so we're still dealing with an original series and a comparison series. You still have to pick a series to compare it with. But then you're going to find the limit, okay? You're going to find the limit of the original over the comparison. You're going to find the limit of the original over the comparison. And if your limit equals to a constant, then whatever your comparison is, whether it converges or diverges, then your series converges or diverges. Okay, so let's go back to part B. What does all of that mean? We compared it to what? P series, which was 1 over the square root of n, right? And then you guys mentioned that by the P series, what happens to this? Diverges. It diverges. But then we determine, well, that's inconclusive, right? Well, what if we do the limit comparison test? We do the limit as n approaches. They ran out of ink.
How?
Great question. There we go. Of the original series over the comparison series, which in other words is the same thing as multiplying the original by the reciprocal of the comparison. Right? And what would that limit equal to? No infinity. Well, what's your leading exponent in the numerator? Exponent. It's 1/2, right? What about the denominator? And what is the coefficient of the leading term in the denominator? Just 1, right? So what's the limit? 1. Is the limit a constant? Is it a finite positive number? It is. Therefore, by the limit comparison test, since our comparison diverges, our whole series also diverges. Okay, so by the limit comparison test, series diverges. So technically you guys weren't wrong. Those of you who said it diverges. But you just didn't use the correct vocabulary, right? Yes.
So if it equals 1, then it's diverge?
If it equals to a positive real number, then whatever your comparison does, that's what your series does.
I thought it would,
So if your comparison converges and your limit, let's say, equals to 1.5, then the original series also converges. Because our test wasn't enough to show.
So if we get a number that's
Positive and real number,
so if we don't get if we get like a negative number,
then it's inconclusive.
then it's still inconclusive?
Yeah.
So but if we get a positive real number, then we go back to compare it, and then our comparison does one thing, the other one does another.
Exactly. That's just basically saying that the end behavior for both comes to a particular ratio.
So the original is always on the top?
Yes. You don't get which one? The comparison test?
No, I don't get why we didn't like this first.
Just because I mean. Wait, I thought you guys always wanted me to show you guys the shortcut first.
Yeah, this is shortcut right here.
This is not the shortcut.
Oh, it's the long version?
This is the long version. So you prefer the long version now? I never understand students. I thought you guys always wanted me to show you shortcut first. That's why I started with shortcut. Nope.
And you don't understand that, what's the point of doing it? You don't know what you're doing.
Okay, so why do you guys think I showed the shortcut first than the long way? The long way for this problem is actually not that long.
Because if it's inconclusive, you can just.
Yeah, this always works. Using the comparison test, using limit comparison test always works.
So those are the shortcuts on the left?
Yes.
Oh, I thought those are like different, like.
Well, you want to use your comparison to something like this.
Okay, I get it.
You want your comparison to look geometric, or maybe integral test, or maybe p-series. In this case, we use p-series, right?
Oh, yeah.
And our previous one, oh, let's do this one again. Okay, this one we use geometric, right?
Yeah.
Sarah.
So what if we do the shortcut, like on the regular?
So if you're doing the shortcut, you have to indicate which one's smaller and which one's larger.
Yeah, like if we indicate it from that, if we can't, is that when we do the long way, like
Yes.
we double check?
Exactly. Yes, very good. You can still use a shortcut, but when it's inconclusive, you have to do the long way.
Okay.
All right, so let's do problem number 1 using the long way, the limit comparison test. So we're still comparing to 1 over 3 to the n, right? And what do we know about this series?
It's geometric.
Geometric, so converges or diverges? Converges, right? By the geometric series. Now, if you don't want to do the shortcut, if we don't want to identify which one's less, which one's greater, or think about whether it converges, diverges, smaller, larger, right? What if we do the original times the reciprocal of the comparison, because I already did my piece change flip. Then eventually it's technically each CC. 3 to the n and 3 to the n. So the limit would actually equal to 1. Since the limit is a positive constant and your comparison converges, therefore your original series also converges. Now here's the challenging part. Are you guys comfortable with finding limits?
No.
It could be someone.
You have to get comfortable finding
Someone,
limits.
yeah.
Okay?
We haven't done it in a while, so you know, I don't remember, but.
All right.
You use ECC global and all that for all limits.
Most limits, yes. Or you guys can use L'Hopital's rule. Do you guys remember L'Hopital's rule?
I forgot it.
Oh, guys. Y'all are, come AP exam, what are you guys gonna do? So you guys are just gonna take the class again in college?
No. I mean,
Who said yeah? You're already telling, you're already defeated, Ava. We don't want that. Come on, y'all. Y'all are smart. You guys got this. Anyway. Alright, what about this one right here? Okay, I don't see any number other than 0 and 1. How in the world do I do this? Okay. Well, first of all, is this geometric?
no.
Can I use an nth term test? Not really, right? Because the nth term test will still come back inconclusive. Because my variable is n, where a and b are positive constants. The limit is 0, so nth term test is inconclusive. Can I integrate this?
You want to?
Not quite, right? We don't know what a and b are. Is this in p-series? So then what are we stuck with? Comparison. What are we comparing it to?
1 over an. 1 over. Wait.
You could use 1 over an, but what about just 1 over n? Wouldn't that also work?
Yeah, sure.
Yeah, that would work, right? We don't know what the value of a is. We don't know what the exact value of b is.
The limit is 0.
0? It's to infinity.
And beyond.
It's bigger on bottom. The variable is n, right? As n gets larger and larger and larger, the whole thing is closer to 0.
Well, why should I?
Because that's the limit. Does that make sense? If you were to plug in 10, 100, 1000 for n, what's happening to the denominator? So therefore the whole fraction is getting smaller, right?
You set the limit.
All right. What do we know about 1 over n? Converges, diverges?
Converges. Wait.
No.
Diverges.
Why?
Because P is equal to 1.
Good, by p series, right? P equals to 1, which is less than or equal to 1, right? So when it's less than or equal to 1, which I forgot to put 1 there, okay, diverges, right? Using the limit comparison test of my original over the comparison, or times the reciprocal of the comparison. Well, what's the leading term in the numerator?
And,
What about the denominator?
and.
an. Just an, right? Just the leading term.
Oh.
What is this limit equal to?
1 over a.
1 over a. And since a is positive, is 1 over a positive finite number?
Yeah.
So what does that say about the original series? It diverges. Very good. A is positive, right?
Why isn't it like?
Well, they told us if A is negative, then conclusive.
Right. So if you can't do any of the tests, you could just put inconclusive.
Yes.
Wait, can you say that again? The 1 over a.
Limit has to equal to a positive number. Doesn't matter what the number looks like. It just has to be a positive number,
Oh,
right?
even if it's like a fraction.
Even if it's a fraction. We are given that A is positive, so we know that it's going to be greater than 0. Right, so by the limit comparison test, which is, I'm going to abbreviate, series diverges. If this is an FRQ question, make sure that you follow through the steps. When you're comparing it to something, make sure you state that it diverges or converges, and by what test. You don't have to indicate that P is equal to 1. You just have to state by P series, 1 over n diverges. Or you can say by the harmonic series. The harmonic series is 1 over n. Okay, it also works with P series. Yes.
Could we also do 1 over a in comparison?
You can, yeah. 1 over an.
That would also just be the P series?
Yes, it will still be the P series. Question. Try the next one. Oop. Actually, let's do this one. Let's do this one. This one's a little bit different. Okay. So once again, is this geometric? Is it, can I use the nth term test? We can always use the nth term test, but would it always give us the answer? What's that limit equal to? 0. How do you know? Bigger on bottom. The square root is less than the square. So will that help us determine convergence or divergence using the nth term test? No, inconclusive. Integral. Yeah, too complicated. I can't use U-sub. I can't use long division. I can't use our trig or integration by parts or partial fractions. We didn't learn how to integrate this, so we got to use something else. Is this P series?
No.
It's not in the form of P series, so what are we stuck with? The comparison. Now, here's the tricky part. What do we compare it with?
N squared. Square root of n over n.
The square root of what?
N over n squared.
Yes, actually, the square root of n over n squared. the leading term of the numerator and the leading term of the denominator. Let's simplify that. I can't simplify that, right? Good, because this is the same thing as n to the 1/2 over n squared, which is n to the 1/2 minus 2. And what does that give us? Which I can write it as how?
1 over n to the 3.
So we're comparing it to n over 3/2. And what do we know about the comparison?
Figure out that.
It is P series. Diverges. So diverges. So this right here diverges by P series. You don't even have to explain why. We know why. We want to know if you know why. Then what do we do? So we find the limit of the original. Yes. Oh yes, thank you. Yeah, I'm just making sure y'all are paying attention. All right. So it is the original series over the comparison, which is basically multiplying by the reciprocal, right?
And the numerator is become n1/2.
Oh, no, we're not crossing.
What is this limit equal to?
So
It will be 1. How do you know it's 1? Well, eventually, if you were to simplify, because all we care is about the behavior, this is going to be the leading term, right? Which we already know it's going to be 1 over n to the 3/2 plus something, or minus something, times n to the 3/2 over 1.
Simplify. The original version is easier.
Right? It's the same behavior. So then, what does that tell us about the whole entire series? Converges. Why? Good. The series converges. Questions?
So did you multiply across or?
I didn't. I just simplified what this behavior is going to look like. Eventually, this fraction kind of will simplify to this right here. This right here simplifies to that. And by each CC, you divide the coefficients.
Absolutely.
Does that make sense? It's not proper math, but it's proper end behavior. Questions?
So basically you just divide the n by 2, right?
Basically. Any questions? All right. Exit ticket. This is your best test. Here's your best test. Bye, Nathan. Good luck. The best test. You ready for your best test? Everyone has to do it.
What?
You have to determine what is the best test to use to determine convergency.
This is
And-
a test.
This is your test. Yes.
So this is the best. Oh my god.
Yes, this is the best test.
I did mine.
Some of these you can use multiple series, but what I I'm asking this, which is the best here. Right, Tim? And I know Tim is also gonna say something.
Third one. Oh, this is
Alright, you guys think you got it?
Wait, what do we think 7 is? P-series is way easier.
7 is alternating.
7 is alternating series? Wait, I thought alternating series was like
Or is it root test?
That's what I said.
What is that?
I don't like that at all.
Yeah, I don't like that.
I'm getting uncomfortable.
Alright, I'm gonna go ahead and end it so that way you guys can see.
Oh my god. Ken was a genius!
I'm gonna convert this aside.
What happens when you take out the 3? We're gonna try to recreate they just take it completely out. And 25 later? I think you're gonna break it down. Because for 7, you take the
Again.
yeah, that's like you can do it. It takes more lead. It takes more lead.
I guess.
The simultaneous skin layer.
I told her it was geometric and she made me.
Alright, very good. A lot of people got the first one correct.
Oh yeah, no, bro.
This one has to be the comparison test. The limit comparison test is not really in the form of P-series.
I'm sorry.
Okay, this one has to be the integral test. Okay, you can't compare it. It's not geometric and it's not P-series. Comparison test. P-series. Once again, let's see. I mean, you can use the integral test for this one here, but remember I said the best test.
Can you?
Yeah, LM.
But it started at 1 though. It's like, if you plug in 1, it's 1 over negative.
But that's okay, you can still. Well, actually, we can't use the integral test. 3. Actually, yeah, you're right. We can't use the integral test because there's a discontinuity between 1 and 3. P-series. Geometric. Why is this geometric?
You can split it.
You can split it. Very good. I kind of did it up here.
What I think is, whenever I see a plus to any of the ends, I just ignore it.
Basically, yeah. Anytime you see a plus or a minus to the exponent, you can technically ignore it. P-series. You can also use the integral test for this one. But again, the